Okay, so discuss the VRTBA. So before, let me just contrast to this ABA. So the asymptotic beta ansatz, right? So there we consider a spin chain with a very large circle, and then we have some magnons, and we diagonalize the spectrum, and we have this beta ansatz equation. Last time we explained that in the case of for the full system with C2 slash 2 times SC2 slash 2 symmetry, the scattering is not diagonal, and in that case you have to work with this nested beta ansatz. But in the end, you can kind of diagonalize this scattering problem in a sense and write this set of nested beta ansatz or the beta-Young equation. Now, in fact, so up to 2006 or so, that is all that was done with the integrable methods. So people try to, after you understood the SL2 sector, you can try to understand the ABA in the larger sector. But that's just about trying to find the spectrum of operators on a single with a large number of field insertions. Now we're going to be interested in want to understand whether this intermediate method is going to be applicable for short operators like the Konishi. And of course, naively, this how the heck do you use S matrix of the magnon to study a short spin chain? It seems that the information is not there. But there is there's a well-known example in integrable relativistic quantum field theory where you can learn about you can actually get information about the spectrum of quantum field theory in the finite space using just the S matrix. So this sounds a little surprising because S matrix is about requires infinite space. You can only define it with infinite space, and yet you can go from S matrix to the finite space spectrum because you have essentially margin invariance. This is not margin invariance in the sense of CFT, but it's a margin invariance in the sense that if you have there's a well-defined Euclidean quantum field theory on a Euclidean manifold, and you can exchange the role of space and Euclidean time. So in the 1 plus 1D quantum field theory, if you so Euclidean quantum field theory with some standard choice of boundary condition, you can compactify this Euclidean time circle, and the partition function on this is supposed to compute the thermal partition function. Right? So it's a space minus beta h. So if you know the complete spectrum of the theory on the infinite line, you can just compute this partition function. Now, so here in the integral theory, the beta ansatz provides a way to access the spectrum on a large spatial circle in its entirety. The same thing is true for integrable quantum field theory. So you can also write asymptotic beta ansatz in a relativistic quantum field theory if you know all the particles. Of course, for this purpose, you really have to get all the states in order to calculate this trace. So it's not sufficient to just look at the SL2 sector, SU2 sector. You have to get all the states. And furthermore, you have to account for all the possible bound states as well. And the bound state in integral theory is usually described by some particular arrangement of complex momenta, let's say, of the particles. So every bound state can be viewed as a string of particles. The word string just means a set of particles such that the complex momenta are arranged in some specific way. And if you have this, then you can exchange the role of space and time, and and so let's say this partition function is going to look like it's called z of beta. So let's say this length is beta and spatial length is L. Right? So this is going to be some e to the minus beta times some free energy function of beta and L. Well, let me write it this way. It'll be some beta times L. It's going to be large L limit. The free energy is going to be proportional to the spatial volume. So, you know, you can think of this as equal to e to the minus, let's say the ground state energy beta times L, right? So this E naught now is the ground state energy on the theory on the spatial circle of circumference beta. I guess you would mention this plus sign here. Right. Now this will tell you about the ground state energy, but you can also get excited state energy in integral theory just by putting some additional kind of particles in here, and they're going to carry some momentum, we'll see that there's kind of a natural generalization of this kind of prescription to also include kind of particle excitations on the finite circle in the integral theory. Basically, the idea is basically that these additional particles are like defects. They're just like the magnons, but they're kind of kept frozen at a given set of momenta, which are to be determined by some kind of consistency condition, and the rest of the magnons are going to be populated in the thermal ensemble. So that's going to be the idea. So this formalism, you know, will eventually allow us to extract not only the ground state energy on the circle, but also excited states. I should say that of course this way of getting the ground state is not limited to integral theories. This is also applicable to non-integral theories in principle. But I think to get this excited states, I'm not so sure if there's a simple procedure. Okay. Now to of course, your immediate objection in trying to apply the strategy to the spin chain system is that spin chain system is not relativistic. So you cannot just swap, you know, space and time. That would make no sense. But what we can do is to consider this so-called mirror model of the integrable spin chain system, where we just declare that the mirror model is defined by the same kind of scattering problem of magnons, but with the same S matrix elements, but the role of sort of momentum and energy are exchanged of some factor of I. So we have the magnons of energy E and P, and we're going to say that this E is I P tilde, and P is I. So let's start with the magnon. This P goes I E tilde, and we view this magnon as related to a mirror magnon of energy E tilde and P tilde. All right, so this sounds like a very stupid thing. Right? So can you really get something out of this? Let me remind you of the formula. So the E dispersion relation was of this form, right? So it's like 16H2. Actually, I try to remember what the coefficient was. Forgot my convention. yeah, 16h squared. Right. So this was our Magnum dispersion relation. And if you exchange the rho of E and P, then you get something that looks crazy. You get some, right? So you get the mirror Magnum had dispersion relation E tilde. We just get by inverting this relation, and the formula is 2 arc sinh square root of 1 plus E tilde squared over 4h. All right. So the idea is that we want to consider here magnons, this is the physical magnons, and over here we have the mirror model. Now, what does the partial function of this mirror model look like? Just as a kind of to get some basic intuition, you would expect that if you have a mirror magnon excitation, right, it has this energy, so it will contribute to the partial function e to the minus beta E tilde. In fact, let me call this, okay, in my notes, I wrote beta tilde, but anyway, you understand what it is. Actually, sorry, let me be a little careful here with my notation. So because previously I used L to represent the actual length of the chain. So let me switch my notation a little bit. I don't think I reserved a symbol for this particular mirror model. Let's see what letter do I want to use to avoid confusion. Okay, I'll just call this L prime. And this thing. Okay, let me call it L tilde. So everything that's tilde is meant to be in the mirror model. So this beta is also tilde. Okay, and we want to identify this beta tilde with L, the length of the spin chain. So L and L tilde are not the same thing. L tilde is meant to be taken to infinity, but this L will be held finite, right? So if you have the excitation mirror magnon, roughly speaking, it's going to contribute to the partial function e to the minus beta tilde E tilde. Let us so how does it look in terms of this? It looks like e to the minus 2L arc sinh square root of 1 plus E tilde squared over 4a. Okay, so this looks like a crazy formula, but let's look at this weak coupling limit. So small h. Remember, h goes like square root of coupling. The weak coupling limit, this function, arc sinh becomes a logarithm, and so the whole thing is something to the Lth power. And if you work this out, it's 4h squared over 1 plus p tilde squared plus order h liquid. So this actually looks like a perturbative correction starting at 2L2 order. Okay, so by some miracle, this logarithm that comes out, it will become expansion. Now, what kind of perturbative correction is supposed to show up? This is and also, if this picture is correct, what we're capturing is some kind of finite length effect, right? This finite length effect is kind of has to do with some kind of particle, virtual particle kind of with where line wraps the circle. And indeed, if you look at this expression, it looks like some kind of L-loop order perturbative contribution. And indeed, you know that if you have this length L, the total length L, then you know, so if you calculate the perturbative Feynman diagrams, right? So the perturbative well, so sort of the kind of perturbative loop, loop corrections would involve kind of inserting some, let's say, versus and propagators between adjacent lines. But these kind of corrections are insensitive to the compactness of the circle. The first time you would encounter a loop effect, a loop correction, to just to the Feynman diagram that calculates the scaling dimension that is sensitive to the compactness of the circle occurs at the Lth loop order, because you have something that kind of wraps all the way around. And the only way to do that in planar diagrams is to have Lth order, Lth loop order. And that agrees with this count. Okay, so that suggests that this is not complete nonsense. That seems that even by this kind of naive, argument, you expect this mirror magnon to actually capture wrapping directions, and that will turn out to be correct. Okay, so that's the basic intuition, and in fact, this was the first piece of evidence. We'll come to this detail later, but the first piece of evidence that this actually works was recalled by this kind of important paper by Schnock and Yannick. Forgot which year it was. 2007 or something. Anyway, I think about 2007, where they took this seriously and was able to actually, after some very hard work, was able to produce the correct wrapping correction at 4-loop order, which has been calculated by the hardcore again perturbative quantum field theory folks. So that was kind of a spectacular test of this idea. Not only that the kind of rough scaling matches, but for the actual coefficients of the wrapping correction was shown to agree. And that kind of provides kind of the basis for this mirror TBA approach. Okay, now let's actually formulate the actual thermodynamics. So basically, what we need to do now is we're going to study the ABA, but for the mirror model. That's we don't have to do too much extra work compared to what we had discussed last time. We basically can take the same set of S matrices. For the magnon, we just need to do this continuation of the momenta to this mirror kinematics. But then we have to kind of put it on this circle with the so essentially sort of the only modification in translating the ABA or converting the ABA of the original magnon system to the ABA of the mirror magnon is that we have to, so you have this e to the IPL factors in the beta ansatz. You have to replace that with e to the IP tilde L tilde, and that's it. That's the main. But I mean, there are other subtle differences, so I will describe them when it's necessary. Okay, so now in order to proceed, we have to understand how to do thermodynamics in an integrable system. So this is kind of the standard thermodynamic beta ansatz technology developed by Zamolodchikov, or invented by Zamolodchikov in 1990. So let me first discuss that. So in the notes, I kind of presented the TBA in the context of the Samira kinematics. Let me stick to this notation. Well, actually, for now, maybe I don't need to bother with the mirror notation. So let me just or not discuss the example of TBA for integrable model with one type of particle. So that the scattering is diagonal, I can use the standard Bethe-Ansatz, and then I will generalize to the multi-particle case, multiple type particle case. In that case, we'll need to use the nested Bethe-Ansatz. The generalization would be kind of straightforward once you set up all this technology. So for now, let me just discuss this. So for this purpose, I'm going to consider kind of some other kind of integral model with only one species of particle, and I'm gonna erase this tilde. I'm just gonna use the untilde notation. Okay. So the Bethe equation. After taking the log on both sides and multiply by factor minus I, you get PKL equals 2 pi nk minus I sum j not equal to k log of the S matrix, the scattering phase. There's only one phase in this case by assumption. Pj k, where nk, so these nks are integers. So for all k. That was the Bethe-Ansatz equation. I just taken the log on both sides of the equation. So we're gonna, of course, be interested in the regime, this L. And then take this L to infinity, and we're going to study the thermodynamics. So at find the temperature. So you would expect, of course, that in the limit of in the thermodynamic limit where L goes to infinity, but at finite temperature, the total number of particles would also be infinite, but there will be some kind of constant or some finite particle density. So for that, we're going to kind of pass to a kind of a continuum version of this equation. We see something similar to this before in this analyzing the classical enormous dimension. So let me introduce a particle density function as a function of momentum. So this represents the particle density in the distributed about to the momenta. Sorry, actually, let's say I can use some arbitrary special parameter. Let's call it me, call it u. In this context, the special parameter is always denoted u. So I call this rho sub particle. This p stands for particle, because later there's going to be some other kind of density. Where this u is the special parameter. We'll write this Bethe equation in the form P of u times L. Let's go to 2 pi n of u. So here the density function is not normalized. So the integral of this is infinite, not equal to 1. Minus I, integral du prime, rho particle u prime, log of s p of u prime, p of u. All right, so that is always very standard. Now, I'm going to take the derivative of both sides with back to u. So I get dp u by du L equals 2 pi rho L of u plus something I will denote by 2 pi integral du prime of rho p u prime times the kernel k u prime u, where the kernel k is just this k is nothing but 1 over 2 pi I d by du of log of s P of U prime, P of U. Okay, so nothing much has happened except that I've defined dnu by du to be rho L. Okay, so this rho L is what we call the level density. So you can think of this integer nk as labeling some kind of except some kind of level. Well, this is just some arbitrary kind of quantum number. The nks are integers. Now, of course, so a priori, this as you order your particles in some way through k, the nks you could order them say with increasing nk. That's up to you. So we'll choose that ordering. So without loss generality, the nk is kind of monotonic with respect to k. I mean, they could in principle coincide or not, and also not every integer is necessarily realized by one of the nks. So the level could be empty, so the level can be occupied or empty, and so this is the level density. Now, if there's some sense in which the particles are fermionic, or depending on whether the particles are fermionic or bosonic, you might have Pauli exclusion or not. And to say whether bosonic or fermionic has to do with usually whether the S matrix, when Pj and Pi are coincident, whether the S matrix is equal to 1 or -1. But usually, if it's 1, it's bosonic. If it's -1, -1 is fermionic. In fact, whether you call it bosonic or fermionic, very often is a matter of convention because there's a kind of a change of basis that can convert one to another. So you can redefine your asymptotic states to change like SPP equals 1 to SPP equals -1. It will turn out that later for application, it's always going to be convenient to view this kind of particles as fermionic. So in the usual kind of convention, where you want this S matrix to have some nice antecedent property, and it will turn out that SPP is equal to -1. Okay. Okay, maybe let me just write it there. So SPP is equal to either +1 or -1. There's bosonic or fermionic. And I should emphasize that when I say that this is bosonic or fermionic, it's as I mentioned, it depends on your convention for asymptotic states. It is it's not really tied to whether it's not necessarily tied to whether these things are described by some kind of bosonic field theory or fermionic field theory. But it's going to have a consequence on the statistics. So this kind of a bosonic S matrix will lead to kind of both statistic in the thermodynamic limits, and the fermion will lead to the Fermi statistics. To understand how that works, we need to now to actually do statistical mechanics. So we need to calculate the particle function, the thermobaric function. And for that, we need to estimate the entropy.
Is this ambiguous somehow related to the fact that in 2D you can like exchange bosons and fermions or something like that? Or
Essentially, yes. It's just saying that you have some. It's because there's a preferred order for the asymptotic states. You have particle 1 on the left of the other on. Have particle 1, particle 2. It asymptotic state. The particle 1 is either on the left, particle 2 or to the right of particle 2, and you can change the relative sign of the wave function. Of the convention for the wave function of your in or out states.
And this can be done whether it's relativistic or non-relativistic.
That's correct. I mean, so far I've not used anything about whether it's relativistic.
I'm asking if you can switch between them.
Yeah, that's also true because it's just a property of, I mean, the Bose Fermi statistic has nothing to do with relativity.
But in our case, we have a preferred basis for the asymptotic states, right? We have the like the
No, you know, you can always change your base asymptotic states. It comes down to what boundary condition you impose. I mean, there's no such thing as preferred basis. It is a basis. You know,
yeah, but we have the basis that corresponds to the any support fields, right?
no. You know, that has to do with the boundary condition. What do you mean? The equals for fields. I mean, the equals, we don't care about the fields inside the tray. They're not even engaged in Marian operators. There's no significance to the fields. You can always relabel, you know, your trait expressions. Okay, so it's standard exercise with statistical mechanics from some combinatorics. You just sort of take some particles and distribute them on the energy levels, do some combinatorics just to see you know, how many ways you can distribute it and take the log and get the entropy. So the entropy is going to be I'm just going to write this in the Fermi statistics case. So with the Fermi statistics, there's going to be positive exclusion for a particle occupying these levels. The entropy is going to be minus rho L minus rho P log of rho L minus rho P plus rho L log rho L minus rho P log rho P. There's a similar formula in the boson case with some sign changes, so then let me not bother writing both. So you can also think of this as the whole density, the particles and holes. Right, so this has a particle hole symmetry, as you'd expect. So log Z is equal to S minus beta E minus mu n, where mu is the chemical potential, and n is the particle number. And we're going to maximize this with respect to rho L and rho. When I say maximize with rho L and rho P, that is to say maximize with respect to this, subject to the beta equation.
Where can we see this like formula for entropy?
This is standard statistical mechanics. I'm just distributing. Yeah, I mean, you can you can just consider, you know, m particles and distribute some finite energy levels and take a limit. There's some combinatorics, you know, factorials, and we take the limit, the log of the factorial, you get this, you know, kind of rho log rho type expression. Okay. If you look at the 1990s homological paper, he has given all this derivation from scratch. Okay. To be explicit, I should write this E in terms of the quantity we have here. So E is the U rho P of U, say epsilon of U. Well, this is the energy of a single particle. For later application, this is going to be the mirror magna. This will be what I called this E tilde earlier. So of a single particle in this our integral model. And N is just the integral of rho particle. Right. Now with that, I have expressed everything in terms of the two unknown functions, rho L and rho P. You just have to do this extremisation problem. Solve this extremisation problem. Okay. Any questions so far? This chemical potential is going to be useful later because essentially there's a question of whether you want to choose this mu to be 0 or pi I, which would allow you to change the fermion boundary condition in time. But it turns out that what we want to calculate is something that's more like the Witten index, not the Partition function. So that's why it's convenient to include this chemical potential. Okay. Now, I think it's a standard exercise to do this extremisation. You have to introduce Lagrange multiplier, of course, because there are constraints. I think in view of time, I'm not actually going to do that exercise on the board. It's more beneficial. I think everyone needs to work this out for yourself to derive the TBA. It's a kind of it's a standard exercise. I'm just going to write the result of this extremisation. So it turns out that there's a bunch of cancellation that happens, and when you actually try to find a solution, so the solution turns out to be the following. We'll define this notion of pseudo energy. Pseudo energy. In some literature, they use the epsilon to represent pseudo energy, but here I've already written epsilon, so just to avoid confusion, I'm going to call this zeta of u in my notes. But in other papers, you might see epsilon for the pseudo energy. This is a very important quantity in this context. So pseudo energy defined as follows. So you take rho particle divided by rho level. Now remember, for the fermion, this is always less between 0 and 1. So this is going to be written as 1 over e to the zeta u plus 1. So it's a bit like a Fermi-Dirac distribution with the beta e replaced by zeta. Okay, so that's just a definition. Okay. Now, again, where's this? All right. So the extremisation of this partition function leads to the following equation for the for zeta. Zeta of u is beta epsilon of u plus mu plus integral du prime k u prime log of 1 plus e to the minus zeta of u prime. There's no good way for me to explain this other than saying you can just do this exercise. That's the way you find. Let me just point out that here, this u and u prime, the row of u and u prime are swapped compared to this. Okay, so this is not a typo. Anyway, but all of this, of course, you can find in some logical 1990 paper. But I think this, he also did do this extremisation explicit in the paper because that step was skipped. But this thing is something that you work out for yourself. So this is the TBA equation. It's a functional equation. So in any case, it's more important to know the result. The derivation you can always supply. It's an integral equation for the pseudo energy. That's what it is. Okay, so it involves, the recipes are, of course, you put in your temperature, you put in your chemical potential, you have your dispersion relation, so you have epsilon, you have your S matrix or scattering phase, which gives you the kernel K. This is a derivative of the scattering phase, so that's a spectral parameter. But this, of course, this equation is horribly nonlinear, like this. And how are you ever going to solve this equation? Well, there's two ways. You either solve it numerically, or you use tricks of analytic continuation. Okay. It turns out that this can be very easily solved numerically just by recursion for a lot of systems. So, for example, if you want to apply this to a a relativistic massive quantum field theory that's integrable, like the Liang model, which is what was studied in Zamolodchkov's original paper, it's very easy to just put in some ansatz. For example, you just assume that you don't have this term. You set this, ignore Campbell actually, you set this to be beta E, beta epsilon, plug it in and just iterate the equation, they converge very fast. I think it's actually under, in some situations, under some in some nice situations, the converge is kind of it's like exponential of exponential. So because well, so anyway, it typically converge very fast. Now, of course, we're not done because once you have done extremisation, you have to plug it back into this formula to calculate the party function. So log of the party function, which up to a factor of the temperature is the free energy, is going to be L times into a du over 2 pi dpu by du of log of 1 plus e to the minus zeta of u. So let's start this formula. Okay, so so let me explain a few features of this formula, which looks kind of funny. You see, the TBA equation does not involve it involves this kernel K, but does not involve this factor here. Okay, I mean, this of course is expected because we have an extensive system, so it has some volume L, and this left-hand side involves L. It better be that pseudo energy is independent of L because it's a ratio between particle and Hall density. So L just multiplies the whole thing, so that makes sense. So once you express the whole thing as L times something, that something is independent. It depends on the particle and Hall density only through their ratio. Which is nice. That's it. Okay, so this PU, of course, is something you know to begin with. You choose whatever you want to use. So of course, you can just write this as d by integral dp. Same thing. So if you choose u to be p, then you can just drop this factor. And that's it. So if you have a pseudo energy, you plug into this formula, you get the free energy. So very simple. Okay, so that's the TBA. Any questions about this? So for example, of course, when Zamolodchkov invented this, his interest was to study RG flow in 2D integrable quantum field theory. The idea there is that if you have a well, okay, if you have this if you can calculate the free energy of the system on this say of a massive quantum field theory at finite temperature, then you can just take the so on a large circle, but at some finite temperature, you can, for example, consider the high temperature limit. So in the high temperature limit, if you imagine there's a CFT in the UV, then the system will be described by the high temperature, by the the thermal party function of a CFT. In particular, the free energy should have to match with the Cartier formula. So from that, you can read out the central charge. Said differently, if you use the earlier this kind of modular relation to convert this to the ground state energy of the theory on the finite circle, in the case of a relativistic quantum field theory, in the limit when the circle is very, very small, you are probing the UV CFT. The ground state energy is just going to be a Casimir energy, so from which you'll read out central charge. So using TBA, you can easily calculate in the high temperature limit the central charge of the UV fixed point of your massive quantum field theory. All right, so this was kind of a remarkable observation, as Zamolodchkov used this to deduce kind of many integrable RG flows. So there's some, you write down some integral S matrix, you discover it's the flow from like the Ising model or okay. Now, of course, we're going to apply this to a mirror model of the magnet. Now there's one important thing I have to. So actually, let me just say that this is supposed to be equal to. Well, let me not even write the iteration from this.
Okay. So this constraint that we have to take into account when extremizing, is that like the analog of like the Liouville equation, like when you usually do statistical mechanics, or?
Liouville equation.
Yeah, I'm just trying to like make an analogy with usual statistical mechanics.
I don't remember what the.
It's
So
like
what do you mean by
it's like a conservation of phase space volume or something like that, or
No. Well, let me see. Is it analog?
I was just trying to translate this into usual statistical mechanics, just to make sure everything like is, or is it like Hamilton equation? Well, that's the
Let me see. Well, I mean, of course, this is about the scattering problem. That's not accounted for by any of the things you just mentioned. But let's see, is there some kind of other this is similar situations? I mean, it is a quantization condition. So, now, of course, if your system is not interacting, this k mu term is gone. And you're left with just the level density and L. I'm not sure what to say. It's a quantization condition. It's like, think of this like Bohr-Sommerfeld quantization condition.
okay.
All right. Okay, so the next important thing I need to say before moving on to the actual model of interest is how to generalize this to get excited states. This already was kind of beyond what Zamalojkov did in his early papers. And this is a story that was understood by Fleury in the, I guess in the late 90s, I think. Erase that side. So as I said, this thing, of course, captures the ground state energy of the system or the mirror system, the unmirrored system, let's say, on the finite circle. Okay, maybe let me start to write this formula. So this is supposed to equal to, as I said earlier, L times E naught of beta tilde. Sorry, of beta, where the E naught of beta is the ground state energy of the system on the finite circle. If it were relativistic, right? If it's not relativistic, it will be the mirrored or the unmirrored system. All right. Now, we discuss TPA for excited state. So we need to add some particles. Now, of course, this is kind of a heuristic. I mean, that's just kind of a impressionist picture. I mean, of course, I'm drawing the Euclidean time here. These are supposed to be particles moving in Lorentzian time. In the integral theory, there's a kind of a huge simplification as how the particles can never be created or annihilated in the scattering process. So if they're there, they just stay there, no matter what other particles are around. Of course, there'll be some scattering and so forth, but particles are never destroyed or created. You can understand the TPA for the excited states just by sort of adding the particles to the beta ansatz, but I view that as kind of part of the background. That's not accounted for in the statistical ensemble. So for this, you can just consider maybe I shouldn't have erased that formula. So you consider the Poynting function in a modified way minus beta E minus mu n plus integral plus integral du rho particle u times sum j from 1 to k log of s uj u. And also max with respect to rho L and rho P. So the idea here is that so think about calculating this Fermi function, and we have some particles that carry some momentum that we view as some kind of a defect in the system, and we're studying kind of a thermal bath of particles on top of that. And the effect of having this these defects is that they introduce some additional phase factors in the contribute to a Fermi function, which can be written in this way. So you know, if you take exponentiation of this, it's just the product of the scattering phases of uj with all the particles in your thermal ensemble. The k here is the number of so k particle excited states. Right, so this k is a finite number. This is the same as this k over here. So this is a scattering phase between the particles you want to excite and the particles in the thermal bath. All right. Okay. So if you do this exercise and repeat the same exercise, you'll find that this expression, once you extremize, is given by the identical formula. L du to pi p of u dp by du of log 1 plus e to the minus z of u. But the TBA equation is modified. So TBA equation, we'll just try this again. Let's go to beta epsilon of u plus mu. We have plus du prime k u prime log of 1 plus e to the minus zeta of u prime. This is the same as the TBA equation, but now we have an extra term minus sum j from 1 to k log of s u uj. By the way, S of UUJ is of course the inverse of SUJU, so I kind of swap them for the minus sign here just so that this S is has argument aligned with this K. But you know, this log S is just minus of that log S. Anyway, so these are some calculations that can easily be verified. And the upshot is that okay. The formula for the energy in relation to the free energy is also modified because of the presence of these extra particles. So in this case of the excited TBA, the formula for the energy that you read off is going to be, so this E beta instead of this E0 beta is going to depend on this UJs. Okay, there's an additional recipe that I have to explain because so far I haven't told you what UJs are. Okay, so far I'm imagining that there's some kind of fixed UJ, but that's not going to be how it works because for the actual, you know, excited states, you don't get to just choose the UJs to be whatever you want. They're not continuous parameters. They're still quantized in some particular way. And I'll tell you what the boundary condition is. This is a part that requires some guesswork. I'm not actually aware of a completely self-contained logical explanation of all the formula I'm going to write down, but you can first guess well, as often how it works in integrability, you first guess it based on some general reasoning, and you try to fix the result by consistency. somehow it's very important in integrability to believe that the answer exists, and then if you believe that it exists, you can try to find it. And it exists in the form that you write. It was before it was minus it was just minus of this thing, the multiplied L, du over 2 pi dp u by du log of 1 plus e to the minus zeta of u. But then you are shifted by the momentum of the particles. The momentum gets swapped into energy when you do this space and time swap. To get the coordinate is I sum of p uj, j from 1 to k. So that basically accounts for the kind of defect particle themselves. Okay, so that's the formula you expect. As I said, there's a bit of guesswork here. I'm not aware of a fully first principle kind of logical derivation of this. Of course, in various explicit models can just check that it's true, and you know this has been checked in numerous ways. Now I have to tell you what UJs are. Okay, so what the equations are? So we have the TBA equation, which is this we call the excited TBA equation. We have this formula for the energy of the excited state on the finite circle, which is the one we want. But then I have to tell you the UJs. So the UJs obey quantization condition. What are the quantization conditions? Quantization condition will say that the quantization condition is such that the thing inside the log, if you plug in u equals uj, it vanishes. So that is to say, 1 plus e to the minus zeta of uj equal to 0. So this is for each of the uj. So of course, it's the same as saying that zeta of uj is equal to well, this one doesn't matter. 2 pi I nj plus 1/2, where nj is an integer. That's the quantization condition. Okay, so one comment is that generally speaking, in the kind of physical situation of interest, the solution to this equation would involve complex uj. This complex value of uj does not lie on the integration contour in U, which is good because if it did, it would be something that's singular. Okay. Nonetheless, in fact, you can convince yourself that you can kind of get this formula from the original TBA for the ground state. If you imagine that you just change the U integration contour so that you include some additional contour that encircles the singularity. And then by integration by parts, you'll see that singularity, the residual contribution just give you this extra term in front. Right? From integration by part. So sometimes people, because of this, sometimes people say that the expression kind of integral system is that sort of all the states are related by some kind of anti-continuation. In this case, it refers to just deforming the U contour, and somehow by deforming the U contour, you can go from the TBA for the ground state to the TBA for the excited states. In general, that's to actually deform the contour is a very complicated procedure, but this is believed to be the general correct answer. Yeah.
So the statement is that this only works for this specific UJ solution.
Oh yeah. Because I mean, you cannot possibly work for arbitrary UJ because the spectrum of the system is discrete, of course. I mean, there's some discrete energy levels. You cannot allow yourself to continue start UJ and say that there's still the energy level. That wouldn't make sense.
This gives you the allowed.
Correct.
Oh.
So the thing is, I started by pretending that I can freeze this defect particles. Of course, they're not actually defect. They're not things you can put in with some frozen or some fixed momentum, right? You don't get to choose that. They are still dynamical things that the momentum will have to adjust and obey their own quantitative condition. So in a sense, yeah. But anyway, that's the result. Yes.
So I still don't understand where this condensation condition came from. Like, why did they take this form? Or
As I said, there's no. It's a guess.
okay.
It's a guess that can be verified in many example models, but I'm not aware of a fully kind of logical explanation of it. Okay, that kind that's from some principal quantization. So you know, it looks a little bit like the beta-ansatz equation itself, but I'm not aware of a way to think of this as actually the beta-ansatz equation for these actual particles, because it's kind of in an ensemble. You know, so it's somewhat kind of the stem ensemble version of the beta-ansatz equation. That's the best thing I can say. In fact, you see, okay, but let me give you, yeah, but this is often how the integrability kind of operates in this field. This is how they can get a lot of mileage, you know, because they have very clever guesses. So look at this formula. Plug this into the left-hand side. Okay, so or take the left-hand side, plug it to this, right? So if you exponentiate both sides, right? If you exponentiate both sides, you see that so the energy and momentum kind of the rho get exchanged. You basically get something that looks okay. So if you exponentiate minus of this, right, and it's equal to -1, it looks just like the beta-ansatz equation. Sorry, hold on a second. Not quite. So sorry, not quite. You have to plug into here and substitute in u equal to uj or maybe uk for one of the uj's. And then you get some. Then it looks kind of like the beta-ansatz equation. So the space equal to 1. There's some e to the beta times epsilon, which can be interpreted as it's like the e to the IPL, but for the mirror P and L. And there's a bunch of scattering phases. But there's also kind of the I guess here you have the phase of the uj with itself, which will give you, the log will give you pi I, and it's exponential, you get -1. I think the -1 gets cancelled. I think that's why you have this -1 here. But then you have this correction term, and this correction term, I'm not aware of a way to think of this strictly as something that's part of the beta-ansatz, but it's kind of some kind of thermal version of it. So it sort of has the kind of right structure. If they wants to have the right interpretation, but I don't know of kind of a completely precise way to say that it has to be this structure. Yeah, in fact, at least in early literature, as far as I know, this is always explained as nobody really tries to kind of derive it by following this line. I mean, it's really always explained as what you get by analytic intuition of the system by deforming the U contour. But why should you get all the states by deforming the U contour? That's what itself is an assumption, of course. But this kind of assumption is often made in the integrability approach, and it's usually justified just by checking. Okay. Yeah. So this is the story that would work for any integrable quantum field theory as well. But let's say with one species particle, we're not going to generalize this to the case of multiple species of particles. In fact, let me now describe this specifically in the context of the mirror Magnon system. So we're gonna start with the beta-Young equation, which is the more complicated version. This is the nested version of the beta equation. And last time I wrote this level 1, level 2, level 3, so we're gonna need that with some small modification. But so far, let me just give a kind of a more general discussion. I'm going to label the levels with capital AB letters. So this equation looks like this: e to the I, P, A, K, L is equal to product over levels, B, product J from 1 to KA. The KA is the number of excitations at the level A. And here, this AB is not equal to KA. We have SBA, XJB, XKA. So all of that, nested beta and that stuff, eventually can be packaged in this form. Okay, so the important to emphasize that. So this is so A and B these are levels in the sense of nested beta ansatz. So this SBA, is not meant to be the S matrix, right? This is just a collection of scattering phases between the level A excitation and level B excitation. So it's important that this is fully diagonal. That's what allows us to proceed. In fact, if you revisit the form of the derivation, the TBA equation, you'll realize that if the scattering were not diagonal, you simply cannot derive a TBA equation using the procedure I gave earlier. The only way to do that is to first do the nested beta procedure and fully diagonal system with these multiple levels, and then you can run the TBA measure.
Should this be like P tilde and L tilde? Or...
Yeah, it will be. But for now, let me just not put tilde everywhere. So there's just no notation. Okay, and also this PA. So this is momentum is PK. And for A go to level 1 and 0 otherwise. 0 for A 2 and 3. I should say that actually, strictly speaking, for this full magnum system or mirror magnum system, we have the SU2/2 left and SU2/2 right. So when we speak of level 2 and level 3, I have to talk about the left level 2 and right level 2 and left level 3 and right level 3 independent, and the tensor that's all together. But that generalization is not hard to perform. Okay, so given that, the TBA equation for is going to be the following. Let me right. So let me write it like this. So we're gonna have. By the way, sometimes I write upper, sometimes I write lower letter, lower AB, and there's no difference. There's no such a difference in that. Like this, epsilon A, mu A, and so here I have sum over B. So prime this will be zeta B, and put some indices on this. KAB. Does KAB come from taking the derivative of the logarithm of SAB? To talk about the particles, we'll discuss the particle excitation later. So for now, let me well, actually, I guess I could write like this. So let me call this a dot uj dot, where the dot represents the appropriate level 1 particles that I want to excite. In fact, to actually apply this, there's going to be a important piece of a recipe that I haven't yet explained, which I'll probably take the rest of today to explain, which has to do with the fact that that the even the nested beta ansatz that we have derived last time is in fact not quite sufficient because we need to understand the bound states. Yes.
Is the spectral parameter U the same as the X's that we talked about last time?
It doesn't matter what you use. You see, you just arbitrary parameterization, right? So it doesn't have to matter what you parameter you use or parameterize it.
But it could be the same X's.
You have to be careful. Well, okay, it could be, but there's x's are there's all kinds of square roots. There's x plus and x minus, which are related by which relation is not single valued. So generally, you have to be very careful with the analytic structure. So it's true that you can use any one of them to parameterize, but you know, we're trying to parameterize can change the analytic property, and it's very important to keep track of that. So the explicit parameterization will be explained. We'll discuss that later, but but for now, this U is general. I mean, nothing I say here is specific to any particular choice of the special parameter. They're going to cancel out because we have this du d by du. All right. And similarly, of course, this formula would be modified to, you know, it would be something like this. Okay, maybe I don't put the dot here. Dot, this represents what the type of particle I want to excite, sorry, this would be okay. I mean, I guess for this, I could write PA. It doesn't matter. It's the same thing. And the quantization condition would be this delta. All right, so so at this point, I will need to discuss bound states before I can actually write down the real TBA equation or the mirror TBA equation for the Nichols force parameters. Let me see what will be whether I want to explain this. Okay, so let me first discuss the bound states of just the ordinary magnets before getting to the mirror magnet. They're quite, as you'll see, they're quite similar. So the bound states magnons. So the bound states of magnons will be completely characterized. Well, okay. Actually, for the moment, let me just discuss the bound states of SL2 magnons. Actually, let me make sure that's going to. Right. Okay. Let's just discuss the bound states of SL2 magnets. The SL2 magnons themselves obey a diagonal scattering, as you might recall. I'll just call this the SL2 sector S matrix. It's the phase. So this is what we call D12 squared, where D12 was one of the 10 matrix elements I squared because you have the left and the right. And the tracing phase will be included in here. So let me remind you this formula for this. It is equal to x2 minus x1 plus over x2 plus minus x1 minus 1 times 1 minus 1 over x2 plus x1 minus 1 over 1 over 1 minus 1 over x2 minus x1 plus times e to the 2I theta x1 plus minus x2 plus minus theta is the dressing phase. Right, so this is the scattering phase between a pair of SL2 magnons. As always, the bound state of the two particles will be detected from the pole of S matrix. Now, of course, you are in the integral theory. You also know 3 to 3 S matrix and 4 to 4 S matrix and so on and so forth. And you can from the poles of those S matrix, you can find all the bound states. So in the integral theory, once you have the two-body S matrix, you can find all the bound states. This is not very difficult. So let's look at that. So obviously, there's a pole at where x1 minus equal to x2 plus. Well, this will give a bound state of two magnons. Very simple. So I literally take P1 and P2, and I say that the x1 minus associated with P1 must be x2 plus equal to P2. And that makes the radial momentum, and there you have the bound state. Okay, so you can think of the bound state as simply the two, the particles side by side, and the momentum constrained by this relation, and that's it. If you want to scatter with something else, you just do this, and do the scattering phase, the product of these two phases. That's the bound state. Okay, so it's not hard to generalize this. So Q magnon bound state. This is what Arjunov and Frolov call the Q particle. It's just a string of magnons such that their special parameters are lined up in the following way: x1 minus equal to x2 plus, x2 minus equals to x3 plus, and xq minus 1 minus equal to xq plus. Now, there's a lot of consistent check one has to in principle perform to make sure that you're in the right physical kinematics and so on and so forth. So there's a lot of work that goes into checking this. And so there's several papers Arjunov and Frolov were dedicated to checking all of this. So I'm just kind of telling you that the nice answer, but you worry about the various different possibilities related by analytic situation. But it turns out that these are the only physical bound states. Now let's talk about the special parameter that Ben was asking about. So we're going to use the parameterization. We're going to write x plus minus of u to be such that x plus minus plus 1 over x plus minus equal to 1 over h u plus minus I over 2. So from now on, this is always going to be the special parameter I use. Okay, so this x plus and x plus 1 over x plus is 1 over h u plus I over 2. X minus is the same thing with the u minus I over 2 here. And h, remember, was the square root of 2 from. Divide by 4 pi. So from now on, this is always going to be the u, and this will be the case even when they talk about the special curve. I don't know when we'll talk about the quantum special curve, but sometime of the summer, perhaps. Okay. Place where I have the formula. All right. So if you start at this, this transition is very nice because you say x plus and x minus relate by shifting u by I, and therefore u is all aligned. You just line up. All right, so this means that this corresponds to ui equals some u plus this u is just some new parameter I'm introducing. U plus q minus 2j plus 1 times I over 2. I is the square root minus 1, and j is the label convention from 1 to q. Okay, so this is kind of the first example that we encounter of what's called a beta string. So the beta string just refers to the string of u's that line up in this way that describes the bound state. Nothing more than that. So this is actually kind of interesting formula because let me keep that. Let me erase one here. This is a kind of interesting formula because if you calculate the dispersion relation, so what are the what is the energy and momentum? So of course we have the formula e to the IP equal to x plus over x minus. Remember the formula, and we had energy for the individual magnum. This is equal to -1 minus 2I h x plus minus x minus. This is one way to write the energy. So now for the bound state, we just have xi plus over xj, sorry, xj plus over xj minus product over j. And the energy is sum j from 1 to q, this thing. That. But now, of course, you notice that if xj minus equals to xj plus 1 plus, so this thing just telescopes, and most terms cancel, you end up with simply x1 plus over xq minus. And similarly, this thing also collapses into minus q minus 2IH x1 plus minus xq minus. Okay, so very simple. And if you solve this in terms of p, you find that this is equal to square root of q squared plus 16h squared sine squared p over 2. Okay, so this is a very satisfying looking formula. All you need to do is replace that 1 by q squared, that's it. And you also read off the binding energy. See, there's a non-zero binding energy in general. Okay. And as I said, now using this picture, so here you have a S matrix element between the q equals 2 particle and q equals 3 particle. You just need to take the product of all of these scattering phases and you get the full scattering phase between the two particles. Okay, very simple.
This is still just for like SL2 set.
Correct. That being said, it's not hard to generalize this to the whole thing because using the nesting procedure. But we need to figure out what are the beta strings for the for this entire system. So that would generally involve not just some kind of level 1 particles with some complex momenta lined up in some way, but maybe it has to be combined with level 2 and level 3. So that's the real content of the so-called string hypothesis, is to say, what are the level 1, level 2, level 3 particles whose complex beta roots have to line up to form the appropriate bound state that will enter your TBA. So that's what this string hypothesis is about. And this was worked out by kind of in this very heroic efforts by Arshinoff and Frollo, which kind of provide the basis of the mirror TBA. So I will discuss that next. I think I erase this one. This relation between the U's. Okay, so now I'm going to discuss the beta strings of the mirror model. So the first type of beta string is going to be the mirror Q particle. So this is just involve the level. Oh, okay. I think I forgot to say an important thing. Okay, let me erase this thing for now. Let me actually write the actual Young equation for the mirror model, because there are a few little recipes I haven't explained last time that I need to explain now. So the Young equation for the mirror model. Of our interest, I'm going to write this kind of more or less explicitly. So now this is the real thing. So p to the so p is now p tilde, l is l tilde. I've written the p tilde and e tilde at the beginning today. We have level 1 scattering. K equals k. A1 is the number of level 1 excitations. Now, here what I'm writing is a formulation of the Young equation. There's a slight variant of last time. The last time I started with the SU2 magna, the defined level, the level 2 vacuum. Now I'm going to work with this SL2 basis instead. They are ultimately equivalent, but for the the things we're analyzing, it's going to be more important, more convenient to work in this with the SL2 basis. So rather than viewing this phi1 and phi2 as the elementary, we start with phi1 and add phi2. We start with we started with phi1 and added like psi1, psi2, but now we'll exchange the role of phi and psi. So we start with psi1 and so forth. So that's what defines the SL2 set. So the level 1 S matrix, the scattering phase will be the SL2 rather than the SU2 scattering phase. In fact, let me mention this last time. Okay. So I've in my notation, I always write this S matrix a priori as a function of the momenta P1 and P2, and now the P's will be I epsilon tilde. I epsilon tilde. So J and K. So essentially, it's still the same object, but I have to now view that as the energy or I times the energy rather than the momentum of the mirror magnet. But of course, if you express this in terms of the x plus and x minus, it was still the same thing. But you have to be careful here. So on the left-hand side, this is really the mirror momentum, which is not the same as the unmirrored momentum. Okay, so that's important. All right, so we have the level 1 S matrix, and we're going to have level 2, L from 1 to K2. This represents the number of level 2 excitations. But we have the left and right SU2 slash 2. So I'm going to use, okay, so in my notes, I use this var sigma, which looks like zeta. Let me write this sigma. This var sigma is indistinguishable from zeta handwriting. So this will be either the left or right, as you refer to the left or right as you two/2. Sometimes in the literature on this, they call it the left wing or the right wing. Later, we the left wing or right wing of the Y system or the Y system, the Herod system, all of that will be referred to this. Okay, so anyway, okay, so sigma. So you know you can have independent left and right level 2 excitations. So now, if you work in this SL2 basis and define the level 1, level 2, level 3 using SL2 basis versus SU2 basis, the precise level, so this you know the higher level scattering phases, the formula is slightly different from the SU2 case versus SL2 case. So last time the formula I gave on the board was for the SU2 case. For the generation to SL2 case, or the alternative version for the SL2 case is similar. The formula given in the notes. Now I'll just tell you what the answer is in this SL2 basis. So remember we had this Y parameter. This Y was a special parameter for the level 2 excitation. Y minus X, Y minus X plus over Y minus X minus. So this will be X plus K and YL sigma, right, so here, L sigma. And then there's a factor of square root of XK plus. Okay, from 1 to K 1. Let me explain this a little bit. So so this whole thing here is the level 2 versus with level 1 scattering phase as a function of Y and P, PK. Okay. Now, last time actually I wrote some formula that's Y minus X minus over Y minus X plus, I think. Or check. Oh, 1 second. Right. It's confusing to read. Yeah. So last time I wrote the formula I wrote actually didn't have the square roots and had the minus plus. That was for the SU2. But SL2, the plus and minus get swapped to get inverted to have this. This extra factor has to do with the change of basis. There's kind of a subtle change of basis that's necessary to account for the fact that the original estimation was written for this dynamic spin chain where the length can change. So when the length can change, the presented form of the Yang-Bax equation is actually not the standard one. Okay, so this is kind of important subtlety. In fact, this is why in Beiser's 25 paper, they call this the dynamic spin chain because the length can change. So the estimation actually they obey what they sometimes call the twisted Yang-Bax equation. So it turns out you can convert the twisted Yang-Bax equation to a standard Yang-Bax equation if you just do a change of basis. I explained this in the notes in some detail, but its effect is that you're going to introduce this actual correction to the phase. So this was checked very carefully in this paper by Artino and Frolov in around 2007 or so, and you know, thanks to this guys, all this kind of was checked and placed on firm footing.
One, we're saying we're no longer in the dynamic spin chain because outtilt is going to infinity, or you're just saying it's a change of basis.
Whether this thing obey Yang-Bax equation or not has nothing to do with the L goes to infinity, right? I mean, I'm just saying that the estimation literally does not obey Yang-Bax equation on the infinite line. Okay, so the change of basis is required just to so that they obey the standard Yang-Bax equation. It is because if you insert a extra z, you're gonna effectively shift all the particles that come after with the phase factor, depending on their momentum.
And we have no sigma for the level 1 because they're the left and right just square. Like you go.
No, this SL2 refers to, this SL2 knows both the left and right.
Yeah.
That's right, that's correct. This is a D12 squared.
Yeah.
Exactly. Very good, very good. So this is a level 1 equation. I have two more, right? I have 1 equals, this is level 2 equation, 1 equals J from 1 to K1. K prime sigma plus Y A sigma minus xj minus over xj plus product L from 1 to level 3 K sigma. There's no level 2 here, if you remember, because the 2 level S matrix is trivial. So S22 is trivial. So I have this level 3. And now we have the special parameter W. Okay, I think I have to erase this space. I've got this W parameter, W L sigma minus Y K prime sigma minus 1 over Y K prime sigma minus I over 2H. Remember, this was the 2-3 phase. W sigma L minus Y K prime sigma. Okay, same thing, sigma plus I over 2H, where K prime went from 1 to K level 2, sigma, and sigma is left or right. And finally, for the level 3 equation, we have 1 equals product J equals 1 to K 2 sigma W K double prime sigma minus Y J sigma minus 1 over Y J sigma plus I over 2H over the same thing minus I over 2H. Okay. Sigma minus I over 2H times product the 3 S matrix. So K3 sigma. So L now equal to K double prime. W L sigma minus W K double prime sigma plus I over H. And the same thing. Sigma minus I over H. And of course, K double prime ranges from 1 to K3 sigma. And that's it. That's the Bethe-Young equation for the mirror model.
Why in this case that the level 1 expectation is scalar is both left and right level 2 expectations?
That's just what it is. I mean, what do you mean? The level 1 already contains both left and right sector.
Oh, I see.
Yeah. You know, this is level 2 excitation of left and right. It just refers to like 2 different kind of modification of the same level 1 excitation. The level 1 excitation is essentially replace a is to replace a Z with a D plus, the derivative.
Yes, but I thought like when we are talking about this Bethe-Young equation, we only talk about the left, like the left-handed part.
No. That was the simplification I said last time. Now we're putting it together. This is the real thing. Okay, so this is the actual Bethe-Young equation we had to work. In some sense, this is kind of actually the most kind of hardcore part of this whole business. Okay, so you know, so I more or less I hopefully explained the logic of how you arrive at this. I think this is kind of the one of the most impenetrable parts of the literature on integrability. Like this kind of equation also shows up in the discussion on integrability for Wilson loops, like in the paper by Sieber and Malacina and so forth. Similar equations also show up there. Yes.
During the first line and the second line, should the Y minus X, one of them should be like inverted of the other, right?
Well, I mean, I think my convention is such that it has already been inverted. So both sides. So there's no You mean this versus this?
Yeah, like,
No,
last
no,
time
no.
we had an S21 and an S21 inverse.
Yes, but I think this is, I've checked, this is correct as, you can inverse both sides of the equation, yeah.
Okay, yeah.
So I think I've chosen to write it
I
the
see.
correct way. I mean, it's not so much about inversion, this is about the relative moment, this versus that.
Yes.
I believe I've checked that this is the correct dimension. The nice thing about Archino and Frolov, okay, so the thing is that actually even Archino and Frolov themselves, in different papers, they have slightly different conventions. You have to be a little careful, but they're mostly consistent, like within the same paper. As far as I can tell, they rarely make any sign mistakes, which is good. The same cannot be said by Kazakov papers. Kazakov, I feel like he must have everything worked on his notes, but then he tries transcribe in the publication, there's like typos everywhere. So, which is kind of unfortunate. But so it's much easier for me at least to read the Archino Frolov papers. All right. Okay. So now we need to discuss what kind of beta strings are there? What kind of bound states are there? And the answer is not really obvious. There's no, the only way to really tell is to just to look for solutions to this equation and see, what are the possible bound states? Let me give you an example, just to illustrate how this works. It's really not obvious. There's no easy way to tell. You just have to look at the details form the solution and see what happens. Hopefully I'll be able to get this straight. Let us consider an example. So consider a mirror magnet with a real p tilde. So in the regime where the mirror magnet has a real momentum, p tilde. Now, if you plug into the formula for the x plus minus as a function of momentum and change into the mirror variable, here you find the following strange looking formula: 1/4h square root of 1 plus 16h squared over 1 plus p tilde squared minus plus 1 times p tilde minus I. Okay. Anyway, like crazy formula pop up like this all the time in this discussion, but somehow they all miraculously work out. This is such that x plus is going to be less than 1. Absolutely going to be less than 1. Okay, so this is something you have to check, but you can see that. So p tilde is real, right? So okay, you have to check, but it turns out that x plus is modulus less than 1, x minus the modulus greater than 1. Now, let us look at this thing here. Let's look at this level 2 and level 1 scattering phase. I'll just write it as yx as y minus x plus y minus x minus square root of x minus over x plus. All right, so the thing I would like to understand now is what kind of bound state I can have that involves, let's say, a level 2 excitation, which will come with some special parameter y. We know that we're going to be interested in a system where we're going to be interested in the thermodynamics of the mirror magnets. So the level 1 excitation will always be populated. So we're going to have, kind of an infinite line with arbitrarily many, arbitrarily large number of Q particles. The magnet bound state, 1 magnon, 2 magnons, so on and so forth. And so in the presence of that thermal bath of the level 1 mirror magnons, we want to ask what kind of level 2 excitation can you actually have that will solve the equation? with finite energy and things like that, you have to have finitely many particles for bound state, of course. So for that purpose, we want to investigate. So first, let's look at this scattering phase, which may not be the phase for the complex variables, of course. We'll look at the scattering phase between a physical mirror magnon, so the mirror magnon in this physical kinematic regime, versus a level 2 excitation with the yet unknown parameter y. So what you observe here is that this thing actually obeys the way this is arranged. So this obeys this 2, 1 yx is its absolute value is less than 1 if y absolute value is less than 1. It's equal to 1 if y absolute value is equal to 1, and it's greater than 1 if y absolute value is greater than 1. I actually had to think a little bit, but this is true. All right. So I want to keep the formula. Try to erase the minimal amount of information. Keep this formula. Okay, so in fact, make some space here. Okay, so we want to ask what kind of why. So in the by the way, in the Artinov-Frolov paper, I think the terminology is that they'll just refer to this level 2 excitation as the y particle and level 3 excitation as the w particle. Just you can use this for your parameter, right? So if you don't know where this comes from, this terminology makes no sense, but that's what they call it. All right. Now the trick is the following. We need to make sure that this particle actually can exist as a solution to this equation when you have in the limit when k1 goes to infinity. Because in the thermodynamic limit, we have infinitely many of level 1 excitations on the line or on the large circle, and we have to make sure we can solve the equation for some appropriate value of y if you are to say that there exists this y excitation. So thermodynamic k1 goes to infinity. So let's look at it in the limit k1 goes to infinity. Let's look at the level 2 equation. So this equation. So the level 2 equation okay, so we got this factor, right? This factor is for a given y with okay, so let's focus on the parameter y1. So let's focus on this equation with k prime. So this equation here for y1, right? So that has this factor. So what is it? It's a product j from 1 to k1, y1 minus xj plus y1 minus xj minus square root of xj minus over xj plus. Okay, so now this factor in the limit k1 goes to infinity for a generic distribution of the level 1 excitations. You see here, if modulus of y is less than 1, the odd modulus is less than 1, and this product is diverge, go to 0, or go to infinity, unless y actually is equal to 1. Okay, so this can be finite only if y1 absolute value is equal to 1. Okay, so that is to say that if you just have this y1 particle by itself, not bound to anything else, then actually it can only this y has to live on the unit circle. So this y is on unit circle. But bound states are possible even if you start with a y that's not equal to 1. So not on the unit circle. Here's an example. Now suppose you have a situation where y1 modulus is less than 1. Let's consider that. So in this case, this factor vanishes. This factor goes to 0. So this 0 has to be cancelled by divergence from this second factor in order to possibly solve the equation. So it must be cancelled by an infinity or a pole from this second factor involving w here. And you see what you need is for the denominator to vanish for y1. So you need w, for some w, let's call it w1, equal to y1 plus 1 over y1 minus I over 2h. Okay? So if you have that, then you have a chance to satisfy the second equation. Now, of course, if you satisfy, you can always do some fine adjustments, so find a part to try to satisfy this equation. But that is required. But you're not done because you still have to satisfy the third equation. If you have that relation, you're going to have some divergence from the third equation. And you have to cancel it with something else. Right? So you see here, if that relation is satisfied, you will actually have the same, this denominator here is the same as the numerator, sorry, the numerator here is the same as the denominator there. Well, one of the factors is the same. So that if that relation is satisfied, you get the 0 from this first factor. The 0 has to be cancelled by the infinity from this factor here. And therefore, well, okay, there are two ways you can cancel. So let me see. So this leads to, so from level 3 equation, you must cancel this 0 by a pole from I think let me make sure. Yeah, either here or here. So need a pole from either some y2 plus 1 over y2 equals w1 minus I over 2h, or another w2 equals w1 plus I over h from down here. Okay, so you need either another level 2 excitation or another level 3 excitation. So it turns out that the second option is no good here, because if you have this, you actually introduce another 0 here that will cancel against the pole, so it kind of undo what you just did. So that's no good. So it turns out this first one is the only option in this case. Okay. So far so good. Now let's carry on this process because all right. So now that so this means that if you have a y1 excitation that does not lie on the unit circle, then you must have a y2. If you have a y2, you have to analyze this equation for y2, for the y2 particle. And you have a similar story. Okay. So if you take the y2 and plug into this equation, you will find that yeah, yeah. You'll find that you already have a zero from this, right? And therefore, therefore you need the infinity from the first factor. Okay, so you need this, and then from the level 2 y2 equation, you need the product of y2 minus xj plus over y2 minus xj minus times square root of xj minus over xj plus has to diverge. This product over j. Okay. All right. Now, if you have, now you got two options. This is still visible. Yeah, it's still visible. Okay, so here you got two options. If y2 is greater than 1, so this actually diverges, then you're good actually. So you can satisfy the equation by some finite adjustments. If y2 is less than 1, then the process continues. Then you're going to get W2, and then you get Y3, and then the two choices, and this process continues on. But in this first case, if this happens, then the system closes. So let's focus on this case. So this is the first non-trivial example of the new beta string that we discovered by just staring at equations. So in this case, what do we find? We find that we need to have y1, y2, and w1. They have to obey this relation and this relation. And that y1 modulus is less than 1, y2 modulus is greater than 1. Okay. All right. So anyway, so this is nice, very important paper, very technical and very important paper by Chernow and Frolov. This, I think, which year was this? Let me figure out which year this was. Anyway, one of the original Frolov papers called the string hypothesis of the mirror TBA or mirror model, I guess. They found all the beta strings. So there are actually several different possibilities. You just like try all the possible combinations and see what works. Okay. So this requires some hard work, but after dust settles, you classify all the beta strings. Let me tell you just the answer now. I think after that we'll conclude for the day. I'll erase this. Okay, so this is in some sense, I think this is perhaps the most important part of the analysis. This is like the core. So once you understand what a beta string is, the rest is just to take thermodynamic limits. Of course, the mirror TBA equation is still going to be very, very complicated, and we're going to need several more lectures later, so maybe in the summer, to discuss how to turn that into a form that's actually solvable, that's actually manageable, even by a computer. Okay. But really, this is the real essential physical input. I mean, like after this is the rest is just mathematical trigger of how to solve the equation. Okay, so all beta strings of the mirror model So let me make a table. Right. So we have the level. So it turns out that there are essentially 4 types of beta strings that you'll find that will be compatible with thermodynamic limits. There's level 1, which is the Q particles. There's level 2, which is the one we have analyzed in some sort of case. Sorry, there's the level 2. This one is the one described from the Y by itself on the unit circle. Then there's the 2 and 3, which is the one we just analyzed. And then there's also a beta string involved just level 3 excitation. I'll give you these some names. So I'll call this the type. So this one will be the Q particle, or let me just call this the N particle, which is the N mirror Macknow bound state. And the next one we call this the Y particle, but they come in this Y sigma type. So they have a left wing and right wing Y particle. And the general thing, the next one is in the terminology of Archinov and Frolov, we call this the YW sigma string with a labeled by the additional integer n. The n refers to like how many iterations you have to do to for like the number of y's that are involved. And then there's also what's known as NW string. Okay, these are just names. Okay, so well, later you give them some symbols in order to write the equation. You don't want to keep writing these things that are kind of unintelligible. Well, the symbols in my notes. Okay, maybe it's not important for saying now because I'm not writing a TP equation yet. Denoted by a solid dot. These are denoted by the cross plus and cross minus with label sigma. This are denoted by triangle, and this was denoted by circle, subscript n, and superscript sigma. This notation will later be needed to write the Y system or the mirror TBA equation. But anyway, these are just some symbols. But let me discuss the actual content. So the actual beta string. So what is the what are the things in here? So the first one, this is the bound state. So we have seen this already. X plus minus S go to X plus minus U plus IS, where S equals minus n minus 1 over 2, and dot to n minus 1 over 2, where n is the positive integer and U is real. So it'd be very important to discuss what is the range of the special parameter on the complex plane. So in this case, U is real. In the second case, Y sigma is X U. Turns out that you can either have a plus 1 or minus 1. We can use this parameterization. So okay, so let me back a second. So I could say that Y lives on unit circle, but for later convenience, it turns out that it'd be useful to split the unit circle into the upper semicircle and the lower semicircle, which can be parameterized in this way: xu to power plus minus 1, where xu is what I wrote before. The x is a function of u, and this u now lives on the interval between 2h minus 2h and 2h. So this is such that this thing completes the circle. Then the next meta string is the one we just discussed in some special cases. So this involves both y and w. So ys plus minus sigma is x plus minus of u plus is, and w s sigma is 1 over h u plus is, where s again ranges from minus n minus 1 over 2 to dot n minus 1 over 2, where u is real. So let me just read this kind of digest this for a second. So in the case when n equals to 1, the minimal case, this is the case we discussed earlier. This example I showed earlier. So if n is equal to 1, S is just 0. So you have y plus and y minus. These are what I call y1 and y2 earlier. And then I got one w. But if you continue that on procedure, you'll find like several of these. So they can like further bound states. They're all listed here. And finally, this case I didn't discuss on the board, but it's in the notes. W S sigma is equal to 1 over H U plus I S, where S ranges from minus 1 over n minus 1 over 2, and U is real. And so this kind of completes the classification of bound states in the system. Now the mirror TBA will be formulated by taking the sort of all the possible excitations of the bound particles or beta strings and write the parting function and extremize in the thermodynamic limit. You'll derive the mirror TBA equation. So in the mirror TBA equation, so earlier I discussed this kind of version of mirror TBA equation with this index, with some extra index, A and B and so forth. So the mirror TBA equation, the index A, B will run over all these labels. Okay, so this you know, kind of big system of equations, and that's going to be a mirror TBA. Now all of this, if you look at this, okay, this is some kind of random list that come out of this hard analysis of our two-number Frolov. But it turns out that by some magic, these things will organize into this T-hoop diagram, which has something to do with the representation theory of PSD to come to /4. Okay, so at this moment, it's completely obscure. Well, why it has anything to do with the supergroup representation? But somehow Volodya Kozakov had this kind of magical realization sort of in the literature, you know, this mirror TBA logic is the logic that I find to be at least comprehensible from the kind of physics standpoint. So you understand, you know, where these equations come from. But then there's a kind of alternative logic, just trying to basically just by guessing. You know, you know, because like people that work in integral systems have some intuition based on studying other models, and they have all these various objects, the so-called Baxter functions and so on and so forth, and they expect that based on symmetry, they should assemble into so and so equations. So that's just some alternative logic to arrive at the Y system, which I myself cannot understand. This is the only logic I can understand, and this requires some hard work, but here it is. So once you have this, you can formulate the mirror TBA equation. I think we've gone on long enough, so I will just stop here for today. And in the next meeting, I don't know I don't know whether it's going to be next Wednesday or some later time. So the next step will be actually to write down the mirror TBA equation. And you also have to look at the excited version of mirror TBA equation, which have this extra recipe. If you look at the excited version of mirror TBA equation, then in principle, you can solve it numerically and get a conition. That numerical solution itself is very, very difficult because all these functions involved have branch cards. You have to be very careful about the working in the right kind of branch, especially because when you work with the beta string, generally all these things become complexified. So this is it's almost impossible to keep track of. It is very difficult to keep track of. Okay, so like a lot of papers by Arjuna and Frolov is just carefully do the integration, and they have all these pictures of how you're going to continue on the complex plane with all these branch cuts. That's the reason why it's very hard. But there will be another layer of development, which is due to the work of Gromov and Kozakov and others, where they later will repackage the mirror TBA into the quantum threshold curve. So that will be yet another conceptual leap, which kind of is in some way kind of finding out the actual kind of solving the mirror TBA equation by repackaging it in a kind of different system that allow you to kind of handle the solution in a much easier way. So it's only after this quantum threshold curve we'll be able to explain how to, for example, extract the strong coupling expansion of the Cauchy dimension. A level mirror TBA is some horrible system of integral equations that are fully nonlinear, and they just have to solve numerically, and even the numerical solution is very hard. Like it's hard enough that, you know, I think in the early days when this was first derived, there was this short PRL paper by Gromov, Vieira, Kazakov, what else? It's just the three of them, in which they claim to have solved the Konishi expression numerically, but then Arjunov and Frolov, were kind of disputing their numerical solution because they say, oh, there's subtleties with numerics here, not, you're not like keeping track of the correct continuation and things like that. So, so the mirror TBA equation is so complicated that it's not easy to just implement numerics. It's not something like you just easily plug into Mathematica, like think about it, like work on it for a day. It's more like something that you plug into Mathematica and work on it for a few months, and then you figure out the answer. Right? So it's that level of complexity. But once you get to the quantum circuit curve, is something that's really can be done like very quickly. So.
Did they get the correct answer of the mirror TPA or?
Yes. It was understood later that mirror TBA is correct if you're careful about the choice of branch. It is correct. So when they had repackaged it into quantum spectral curve, they did check against mirror TBA numerics. So that works. But the point is that the mirror TBA numerics is something that's very, very hard to do. It's something that you need a team of graduate students to do. The quantum spectral curve is a numerics that apparently like Gromov can just do in real time in the seminar. So yes.
So the y plus minus one with red line, those are like inside or outside the unit circle.
That's correct.
And so do you need like half of them to be plus and half of them to be minus?
Let me see. But it is the half of the plus and half of the minus. So the S is the label, arrange this, and this notation means that I have ys plus and ys minus.
Oh, okay.
That's what notation means.
I see. And then another question, in general, like, these are the bound states, but I should still think at level 1, 2, and 3, I can have as many as I want,
Oh yes, but the way the TBA is going to work is that we're gonna allow arbitrary number of this, right? They're going to subject to this the constraining equation, but then we calculate the partial function, the sum of all of them. But of course they are subject to. They're still subject to this nested beta or the beta-Young equation. I don't, of course, here I wrote the beta-Young equation in terms of the elementary excitations, but you can just literally replace this with the product of the string of those things, right? I mean, it's the same thing because the S matrix just factorize.
But like, for example, the Y particles are just the level 2 excitations, right?
That's right.
So I could have as many as I want of those, but they just wouldn't be bound. I can't bind 2 Y particles by themselves to something.
That's correct. So the point is that all the bounds have been taken into account already by this table. So you just have these particles that are freely propagating. Well, not freely propagating, but they still scatter. Okay, so you can, if you have a particular state that involve 5 of this kind of particle, 10 this particle, and 15 this particle, you just plug all of that into the equation, and you get some big equation. So that's what it is.
And also last time we discussed, like, I think it was when we started with level 1 being SU2, but the phi 2s were like a bound state of 2, like psi 1 and psi 2 or something.
Yeah.
Are they one of these or?
Well, any bound state that actually will survive thermodynamic limit must be included here. So I'm not sure if it's exactly in terms of the. I mean, I think it's not quite accurate to, because the bound state are really this magna bound state that's from M particle. So the basic bound state is this M particle thing.
I guess we said the phi 2s like don't survive as asymptotic states, so should I think of all these bound states do survive as asymptotic?
Yeah, that's correct. That's correct. I mean, I wrote the dispersion relation. Yeah. So it's a real thing.
So imagine if I want to calculate the energy of some state with like some n particles and y sigma particles. what is the exact way of?
Oh, the energy is just the sum. I mean, the energy is the sum of the energy of each integer one. It's just additive. I showed you the example of the Q particle earlier. Was an example, right? I literally just added up.
Okay.
Right? You just take the energy of integer. That's how that's partly what I meant by this picture of the scattering. You literally can think of this bound state as a few particles side by side. They just have this particular arrangement of the momentum.
Oh, I
So
see.
the momentum is complex.
I see.
So the complex momentum, this reflects the idea that the wave function kind of dies off in with better relative distance, right? So it forms bound state. Anyway, yeah, this is kind of I would say like probably the most painful part of the integrability story. Like once you understand this, the rest, okay, actually manipulating the mirror TBA is also kind of painful, but there's a little bit more pain, and after that, when you get the quantum vector curve, well, everything becomes much more elegant. But this stage is kind of maximally difficult.
But it's also maximally interesting, right? This is like extremely impressive.
Yeah, it's very impressive. It's very impressive stuff. But the derivation of the quantum vector curve from the mirror TBA is, I would say, equally as impressive. There's yet another layer of, even though you can say that level is you're just manipulating these equations, you already know what the equations are, but you really require some kind of ingenious insights, partially borrowed from the worksheet intuition that tells you how to actually find the solution to these equations. It's actually, it's hard to explain. It is one of these very technical things that's hard to explain without actually writing it down, but as author with integrability, like the magic is in the details.
So what does the worksheet tell you about this quantum spectral curve? Like,
it tells you how to set up boundary conditions for the functions that enter. So when you solve this integral equation, sometimes it's very important to know what the boundary conditions are. We'll see that the so-called Y system is a repackaging of the mirror TBA equation, but the repackaging can lose some information. And in order to actually implement the Y system, let's say numerically, if you want to solve it, you have to impose some boundary condition. It's actually not easy to figure out what the boundary condition is. So the Y system itself is actually not very easy to work with at all. In fact, to the casual observer, it's not even clear what it's actually good for. In fact, when I was studying this, the literature initially, for a long time, I just cannot understand what the Y system is used for, because okay, you can say that this the pseudo energy obey this Y system equation, which follows from mirror TBA. But how do you actually use it? Because you still need some additional boundary condition, which is by no means obvious. In principle, the mirror TBA tells you, but it's very hard to figure out what they actually are, unless you just solve things numerically. But when you package this into a quantum spectral curve, there's some nice way to say what the boundary conditions are for this involved, sort of at a large spectral parameter. But that requires some worksheet intuition. It requires understanding that you can kind of swap ADS5 and S5, that kind of things. It requires understanding that you can sometimes swap spin with R charge, and even analyticity in spin. Even some aspect of radio theory is required to provide some ansatz, then you can use the ansatz game and then solve the equations. So yeah, it's the whole thing is very deep, but also very, very kind of clever. Use all kinds of physical inputs. It's not like you just try to analyze some stupid hard mathematical equations. It's more than that. You really you need some physical intuition to guide you every step of the way.
You mentioned at some point string hypothesis, but actually was.
Yeah, the string hypothesis is just that these are all the beta strings.
Okay, so it's they found these and then they said we are assuming these are all of them.
Yeah, that's right.
It wasn't an input to finding.
It wasn't an input. I mean, it's actually kind of funny to me that they call this hypothesis, because by the standard level of rigor of integrability, it's pretty robust. I mean, you really just analyze all the possibilities. It seems like these are all they are. So there are many other assumptions made. I don't know why they specifically refer to this as a hypothesis. But I think this comes from maybe some other literature, as other kind of part of interoperability is the name kind of has stuck. You know, because this beta string actually, they say that this whole thing is similar to the beta string of this Hubbard one-dimensional Hubbard model. I mean, I don't know the one-dimensional Hubbard model. I don't know what the solution looks like, but apparently, like, it's very similar. So that's how they were able to kind of arrive at this result very quickly, because these people know the Hubbard model.
So how did Arukinov like know Hubbard model? Were they working on Hubbard model in the 90s or something?
Well, I mean, you know, the people had a good training in the Soviet Union. Better education. You know, all this, a lot of the important work on interoperability are by, you know, Eastern Europeans, like people from Hungary or like Poland, you know, right? I mean, you know, it's this kind of some kind of Eastern European tradition.
Right.
In the tradition.